So thank you, Stefan, for the introduction. So I would like to first thank the organizer for getting this summer school together. What I understand is a lot of work. I really enjoyed so far. I would like to also thank the audience for taking your time to be here today. It's quite early, and I guess a lot of you went to the Calanque yesterday, so you should be quite tired after, I don't know, having some beers on the patio. So thanks again for being here. I will try to make this as painless as possible. So the first thing, I know that it's a very diverse audience. So I will just suppose that you have fairly basic probability knowledge and stochastic differential equations knowledge. If you have a question, please don't hesitate to stop me so I can make sure that we are all on the same page. Okay, let's start that. Okay, so the few issues with the slides. Well, anyway, so today we'll talk about like scientific machine learning, but in a fairly different way that it's been done so far. So today we'll focus on first dynamical systems, and the second we will try to go a little bit further and dwell into generative AI. I hope this generative AI, as basically like you can think ChatGPT or like a DALL-E or anything that generates images or text, can be used for scientific computing. This is most of this is work in progress and very early research. Now, I mean, when I was a professor, this is the first thing that we're always told to have in lecture. What's the objective of this lecture? So the first thing is like I will try to convey what is our take, at least a part of Google research or my team in scientific and machine learning. I will hopefully give you a fairly small introduction and hopefully as self-contained as possible about these technologies called hybrid networks that you will see in a moment, and diffusion models with applications for scientific machine learning, scientific computing. And hopefully, given that you will be, most of you will be here for 5 weeks doing the research project, hopefully I will give you some tools so you can use afterwards for your project. Questions so far? Everything good? Let's continue. So this is the outline, so 3 blocks. So given that you have already very good introductions to reduced order models by Olga and scientific machine learning by other speakers, I will try to go a little bit fast in the first block. So this is going to be mostly a presentation style lecture. And the second and third block, I will just go to the blackboard and go slowly. So be sure that everyone is on board. So Martin here will give you a computer lab later. We'll lead a computer lab session later today. In this case, will be mostly about learning a little bit of JAX. I know that most of you use PyTorch. Hopefully I can convince you that JAX is a very good alternative, particularly for scientific machine learning. And you will have a few things about Langevin dynamics and diffusion models. So you have questions, Martin is here in the first row. Okay, so let's start with the first thing, who we are and what we do. So I realized that, again, this is a very diverse audience, so I wanted to be sure that I'm fairly diverse and non-linear trajectory myself. So what is the point of these slides is basically you can see that throughout my career I've been doing seemingly random things like chat optimization, web propagation, scientific machine learning, Navier-Stokes. And what I want to convey with these slides is scientific machine learning is so new and it's so in diapers that actually having a very diverse background as this audience actually is a very rich feature to have. Why? Because you can have things coming from every direction to attack the one problem. And there's the richness that hopefully I can convey today. And then, well, other things like being in academia and being in natural labs, so it's a little bit of a hodgepodge of everything. Okay, so how we are, so we're a fairly small team at Google Research. So we have computer scientists, mechanical engineers, mathematicians, and I don't remember what else. So for us, it's like if you want to corporate language, our mission is to basically develop new foundational technologies, which mean try to push crazy ideas and see what is actually can be done. So that's a little bit the advantage of being in industry, that you have time. You can really try to push a little bit of crazy ideas and see if actually how far you can get them. So what we do is we have main 2 focuses. So the first one is, let me see, which is probabilistic modeling. So again, this is, as I was told before, is try to leverage all these new generative AI type of tools to scientific computing. And we think that perhaps this is the real field in which machine learning can really, really shine, because it's well known that all the sampling techniques, once you have UQ, once you have probability distributions, your problem becomes so high dimensional that it's very hard to handle. And machine learning is, in general, is very good at dealing with high dimensional things. The accuracy, you could claim that it's not great, but when you do probabilistic approaches, you're not looking for 3 digits. As long as you're in the ballpark or you have approximation of the posterior, you're fine. And the second part, we are also very focused on weather and climate. And you can see the atmosphere is like a gigantic dynamical system, which is chaotic and have some transport equations, so transport phenomena. So we also focus on that. So as I told before, even though we do scientific machine learning, our downstream application is a really weather and climate. Okay, so just to basically bound a little bit the conversation, I would like to see like machine learning by tasks. So I'd like to think about 3 main tasks. So one is classification. So what is classification mathematically? It's basically learning a partition of the domain. So you have a bunch of points. You want to see which are the cats that are solving together, dogs are together, and so on. The second one is regression. This is basically learning a map that can be high dimensional. And the last one is generation. So this is basically learning a distribution. So today we will go in the second and the third. And what is also the point of this slide is showing that these problems are fairly new. They have like a very, I mean, you could see, or most likely you've seen all these applications in the internet. But nonetheless, these are problems that have been in the numerical analysis community for perhaps 50 years. And we do have a lot of tools to handle them. The issue here is that machine learning has like much higher dimensions. So pixel-wise, I mean, megapixel tends to start to become very, very expensive. Okay, questions? Clear? Yes? No? Continue? So again, this is again trying to a little bit higher level. So for us, scientific machine learning is about like a 2-stage problem. So one is try to embed numeric analysis computational math techniques to enhance ML techniques. And this is basically what was told yesterday, the day before. And the second is this enhance ML techniques to solve scientific problems, particularly the ones in high dimensional. So keywords here, insight that comes from mathematics. And second one is high dimensional problems. Now, I will hopefully make my point. It's like a little insight, actually, in these models can go a very, very long way. And what else? Okay, so let's delve into the first part. So what we want here is to basically learn dynamics. And if I were to do like a very broad separation, it will be physics-driven. In this case, basically, you have solve PDEs, as you see Tuesday. You can do learning operators, although in this case, physics-driven and data-driven can be both these operator type of learning. The other one is data-driven, so reducible models. That's on Monday. And what I want to present today is the same problem with a quite different approximation. So in this case, we will use this what they call hypernetwork. So what is a hypernetwork? Is basically a network that generates another network. Or in this most classic fashion, it's a network that generates the weight of another network. So instead of having to run an optimization problem to learn the weight, what you can do is basically just have one network that generates those weights. Perhaps not optimal, but close enough that you can use them. And the second one is this NERF. So NERF stands for neural radiance field. It's not these toy guns. So what is this? I think I have a picture. So basically what they do is they try to learn a 3D representation by slides. So basically you give us a slide or images, for example, of this caterpillar truck, and then you try to reconstruct the full image. And they're being fairly successful in machine learning. So let me see if this works. So you have these flowers, and basically you have a few of the samples, and then you can do is basically move around fairly efficiently. And this only generated by a few samples. So you can see that this is very useful, for example, for museums or for architecture, in which you can take a few pictures of a building, and then you can explore it very, very efficiently. Now the question is, how do you translate this to machine learning. So you can think this as basically trying to learn snapshots of a dynamical system and then try to interpolate through them. Wait, does it? No. OK. That's exactly what we're going to do. So what we want to model at the end is these complex time-dependent systems. So we will have our assumption that, the task is I give you a state. Just imagine like the state of the atmosphere today. And then you want to learn or want to predict what's going to be the state future date. In this case, it's a time t later. So the main assumption here is that we don't know the model. I mean, what I will show you today, we know the model. So we want to have some idea of what is going on. But in general, you don't know. So imagine like the atmosphere. You roughly know that some equations are present, but you don't have access to all the scales. So the only thing that you can see is not a full complete picture. So what I like to see about this is like this is very similar to trying to learn the rules of a sport just watching TV. So I don't know how many of you are familiar with American football. So I've been in the US for like 15 years. I still don't understand how to play it. But the point is basically, if you sit on your TV and you watch a game, many games, I don't know, like 1 year, can you basically learn the rules? And then if I give you initial condition of a game, can you generate the game or something that's realistic, as you can say it? So that's basically how I like to frame it. I don't know other sports that are that hard. I mean, cricket maybe. But anyway, I found like American. That's my point. It's like so okay, it's clear. So basically, we'll show them the algorithm a bunch of videos, and they will try to learn the rules and basically generate other videos that are realistic in the sense of a statistical list. And why do we care about this? Of course, like we have these very weather and climate applications. We have, for example, heat waves that actually are waves that propagate, and then other meteorological phenomena. And what is the emphasis that we'll do today? Again, you learn model from data. You don't have access to the PD. You have access to some physics that you will add as an inductive biases. And what we'll try to do is like, what is the trade-off between sampling and inference efficiency? And you will see there that a little bit of mathematics actually goes a long way. OK, so first, is this clear? Otherwise, hopefully it's clearer later. So what is the setup? We have a time-dependent but unknown PDE. So this is, this is early research. So basically, you have a PDE, but then you close your eyes, you say, yeah, I don't see it, just see data. And what you have is snapshots. So basically, for each initial condition, U0, you will generate a trajectory, and then you will have a snapshot every certain amount of delta t. And then you will have a lot of these trajectories. So how they're generated, basically, you choose the initial condition from certain distribution. This is, in general, it's a little bit tricky to choose this distribution, as it was presented yesterday. So in this case, it's going to be very, very simple. And then you only learn you only have access to this trajectory data. So the good thing about it's not just random samples. You have a sense of time continuity or time direction. And what we want to do is two things. So we're going back to Olga's lecture at the beginning. We want to have a compressed or latent representation of these states. And second is like, can we learn the dynamics? So we don't only want to compress the states, can we learn how it evolves in time? Now for this F, I was told that I have to write equations, so be sure that there will mostly three systems. So So we'll have three equations. So the first one is, I guess you know fairly well, Burger's equation. So this is T U minus 1/2 partial x u squared. And in this case, people normally like to use the viscous one. So you will have some viscosity. And this is it's fairly easy depending on how large is this factor. So this is kind of the step 0. So everything that you do, you have to solve this equation. If it doesn't, it's very, very bad. This is kind of the like kindergarten for your algorithms. The second one is Kuramoto-Sivashinsky. So we will just call it KS. And this is, let me see that I have the correct. OK. So this is going to be partial t. U is the same, I think it's 1/4 here. Partial x u squared. and then you have minus v plus. So this equation is the prototypical equation for chaotic systems. So what you have here is a additive term. You have anti-diffusion, so basically this is going to make it explode, but you have hyper-diffusion, so to stabilize it. So the point of this is like the prototypical system for chaotic system. I mean, unless you go Lorentz 63, the simplest one, this tends to be the second one. And the last equation that we're going to handle today is called the KdV equation. And this is slightly different. So first, I think it's 1/3 partial x u squared. So what is the issue with this equation? That is a dispersive equation. So basically, all the velocity of the wave depends on the Fourier component. This looks like a very simple, very toy problem, but it turns out that is solving even these problems with machine learning are not as simple as you would expect. So I do agree with Sid's comment yesterday that 1D is fairly simple. You can do numerical methods, and normally they're much better. But even though when you have things that are chaotic or you have dispersive, actually it's not that simple. Many of the regular methods that have been developed in the last 2 years, they tend to fail, even in this very simple toy problem that I think is being solved in the 1700s. But anyway, we will try to do this and hopefully convince you that you can do something with that. So now why we chose these equations. So this is what Olga suggested in the first lecture. This is due to the Gomer width. So I will just give you a little kind of animation of how this works. So basically this tells you the distance between the best fitting n-dimensional subspace to a set of points. So suppose that you have this point M. So in this case, they're collinear, so a line is enough. So in this case, for n equals 1, you already have a 0 distance. But what happens if you move at this a little bit? So this is not the part inside is not satisfied. So you have to move a little bit your linear space. This is one that will satisfy the minimum. In this case, you can see that for n equals 1, it's not 0. But then if you want to increase your dimensionality a little bit, like a plane, now you have 0 because every point in this M that lives in this space. Now, if you increase the dimension, like n3, 4, or 5, it always will be 0 because this is basically already fits all the points. Now, why do you want this? Is because when you do like a reduced order topic models, you want to create a trajectory that lives inside this plane. So for a given dimension, capital N, this number here will give you basically the best L infinity approximation you can have for any dynamics. Why? Because then, for example, you move this a little bit, you will be very off. And this, all this, well, I don't know if you can say, but this type of distances, the maximum is going to be achieved by this manifold, or by this hyperplane. And what we want here is basically have m's that as you increase n, the distance decays very, very fast. And why do we care about these equations? Because it's exactly the case. So if you are in Rn, basically an SVD is good enough. So what we'll do, we'll take two equations. We're going to parabolic equation on the left, and the KdV equation on the, I think that I'm sorry, the 3 here. So you can see like parabolic equation is very simple. You start for something, you lose all the information in the diffusive. KdV is much nastier. So basically you have these waves that propagate to the left and right. They collide, they create ripples, they propagate the ripples. So it's quite nasty, even though it's a very simple equation. And you will see that when you have M, will be basically a snapshot. So you will take your trajectory, compute the snapshot, put it in a matrix, and then in this case, you can compute the n width just basically by the SVD. You will see, well, Olga showed this Monday, if you have a parabolic equation, this decays extremely fast, exponentially fast. So that's fine. If you have something that is hyperbolic or is direction dominated, this decays much lower. It decays 1 over square root of the dimension. So this means that if you want to approximate this bilinear space, the left one is very easy because you did a few modes to approximate it, and then run your dynamics in this, reduced hyperplane. But if you have this one, it takes you many terms to actually to reach the same level of accuracy. So, for example, if you want to do apples to apples, so okay, these are not. So you want to have like 2 digits. So you need, I think, like 4 elements here. If you want to have the same, you need around 50. And this actually goes higher and higher when you have to do for different initial conditions. So is this clear? So these equations, well, Burgers is for least, but this equation, the issue is that they are in the, yes?
Good morning. What do you have on the x-axis?
X is the eigenmode, and in the y-axis is the singular values.
Okay, thank you.
Okay, is that clear? Yes? Questions? No? Okay, so everything that we'll see today are in the right column. There's basically these 3 equations, well, unless this is very high. And the point of that is you observe these transport-dominated problems in nature, and they're very important. And traditional methods, they don't work that well with them. So then there's a few ways to do this. I think, wait. Okay, we'll just give you the, sorry, we'll just give you like the punchline quickly. So we're going to do, instead of trying to do any linear approximation or quadratic approximation, as basically all I was saying Monday, we'll just go full machine learning version. So we've been hearing that, well, neural networks are universal approximators, they're very good and so on. So let's use that. Let's just represent your snapshot as a neural network. So the issue with that is then, would you evolve if you just have the neural networks as your input? What you will evolve are the weights of the neural network. So then you have to basically build an evolution equation for the weights. So that's the punchline. Now you can go to sleep if you're tired. Now let me also put a little bit in context. So I like to think that for scientific ML, in particular for dynamical systems, you can divide all the methods in 4 big groups. So the first group is what I like to call physics, hybrid physics ML. So in this case, you do have access to the evolution equations, but perhaps they're too complicated. Let's just think whether problem, or you only are afford to run in a very coarse resolution. So what you will do is basically add a machine learned correction to that. So all of these methods are in that category. Then you have operator learning that we already saw yesterday. Then we have these other ones, or I like to call them neural ansatz. So what they do is basically that is basically what Yin Zhao talked about Tuesday. So instead of having a linear system, you just change your representation by neural network, and then you need to how optimize it. How this is done is usually using like a PDE loss or physics-informed loss. And the last one that I like to the category is basically purely learned surrogate. So in this case, you have no idea of the equation, you have no idea of anything, and the only thing that you want to do in general is to have what they call an autoregressive problem. So let me just right here quickly, I mean, this is very simple, but just to be sure that we don't forget. So let me put it here. So what do I mean autoregressive? So this is nothing more that you have un, let's see where is un plus 1 is just going to be a function of let's call a network f with some parameter theta of un. So this is basically you want to learn. You know the present, you want to go the next steps into the future. And these purely learned surrogates, normally they are in this setup that we will also use today. So now, what I will talk about, where does it stand? It stands in the middle. We call dynamical weights. It's not the best name, but at some point it's stuck. So this is going to be also this type of autoregressive problems, although with a twist, and we'll have a neural ansatz. So you represent your state by a neural network. Okay, I think that I've repeated myself enough, so let's go a little bit faster, unless people have questions in the audience. No? Okay. So this is another way of placing the problem. So I like to see there is basically two axes. One is how much information you add to your. Oh. Okay. So what I like to see in these like two axes is one is how much PDE information you add to the problem and how much data you rely on. And the second one is what type of your how your representation looks like. So the one's like mesh-based, and then you go to functional ansatz. So basically, this is a neural network that uses an ansatz. So you can see all the way to the top left, you have just regular finite elements, finite differences. So these, you have no data. You only care about the PDE. All information is PDE-based, and you are fully in a mesh. And then you have, these are not all of them, but these kind of like the, I would say, the more important ones lately. And what we claim here is like we're doing the crazy idea that will go all the way bottom right. So fully data-driven and fully functional. Okay. Okay, this is weird. Oh, yeah. So going back to the setup here. So I told you it will be autoregressive. So normally this is called this encode, process, decode type of approach. I'll already presented this. So imagine that you have physical space. You have a trajectory. So you go from ux0, uxt1, uxt2, all the way to the uxt, where t is your horizon. And then what you want to do is basically start with this and try to create a representation that is compressed or latent space. And then what you're going to do is try to evolve this latent space and then be sure that this new latent space corresponds to the next timestamp. And then you will go back. You will have this theta 1 that is the latent space. You go to theta 2 and so on. And this is how normally you work. So basically you go back and forth between latent space and physical space. And this is, OK, sorry about this. I should have changed the notation. I completely forgot about this. It's called beta. So this basically you will do is un plus 1 is going to be, let's call like encode un. So this is going to be your theta n. Then you will process it. So this is when you go from theta 1 to theta naught to theta 1, and then you will decode. So in this step you have, OK, this is not great. Let's put it there. OK, is this clear? No, yes? Yes, no? No, OK, it's not. So basically, a typical autoregressive model will go OK, let's follow that notation. So you will ux0, so ux tn plus 1. You just have a neural network that does x tn. So this is normally would be. The advantage of using this type of approach is that you can basically reduce the dimensionality and do the processing in a reduced dimension. So you want to do, instead of using this, you want to take this guy, so ux tn. You want to have like a certain encoder. So this will generate this theta n, which is going to be lower dimensional. Then you want to process it. So this is going to have theta n plus 1. And then you want to decode it. So this is going to give you EU x tn plus 1. Is it clear? Yes? Yes?
Just a quick question. Thank you. Just a quick question regarding free operators. Which of them you're gonna learn? Are there some of them posed a priori, or all of them are going to be learned?
All of them.
All of them. Thank you.
Okay, so good question. So let's suppose that you have beta, beta, beta. So in this case, you want to be as general as possible. You want to learn everything. I was telling before, let's go crazy with machine learning, so everything can be learned. Questions? Now, is this clear? I will assume so. So, sorry, I lied. Okay, so what is the issue with this? Is that you may realize that you need a uniform discretization in time because you basically fix your step as you do this, which can be good, but in general, if you want to do, for example, weather and climate, data comes you at a different stream. So you want to be able to basically stop mid-time and assimilate some data or do some operations. The other issue is that you have to really go back and forth between the ambient space or the physical space and the latent space at each time, which can be costly. And the main issue here is that this usually becomes unstable. So basically, when you do this F operate over and over, you start to accumulate errors. And the issue when you accumulate these errors is that you slowly start to veer off of your training data. And once you're out of the training data, basically you become unstable very, very quickly. So what we propose here is a fairly different way of thinking about this. So instead of having to do a step-by-step in the latent space, we'll say, well, let's take your UX naught, let's encode it once, and instead of having to go step by step, let's create a dynamical system, or let's learn a dynamical system in this form, theta dot equals to some neural network of theta, and then integrate those. So if you have this term, you can use your favorite Runge-Kutta or whatever integrator that you have, and you can basically integrate in time as long as you want. And then you only go back to ambient space when you want. So you don't have to go back and forth. You can remain in latent space as long as you want. Well, the advantage of that is that you pay is much, much cheaper because the dimension is much smaller. And then you roll out, you integrate until you need it. And then at the horizon only, you go back and you decode. And now this encode decode is a little different than I would have here. So that's why I have different letters. So let me just write it here quickly, so we don't forget. So in this case, this lambda, capital lambda A, it will take some point in UXI. So you take some samples I will see in a moment. And then this will give you the weight of a network. And our decode, basically you will have a network, so you have the theta t here, and then you can evaluate this and every x point, and this is going to approximate u x comma t, let's call it tn. So what I mean with this is basically this capital psi is going to be a network whose parameters will be theta, and then you can evaluate at every point of t. So this is, you can think about like a separation of variables. So everything that is time dependent is going to be theta, and then you can sample whatever you want. So I will, hopefully in the next slide, this is going to be clearer. And what it would do, okay, what we want about this is the model, everything is fully learned from data, so you will see in a moment. And what we really want is to have something that is continuous both in time and space. So in this case, you can, your integration can be stopped at any point, and then you can sample afterwards, whatever you want. So in this case, this X can be done basically anywhere in the domain. So you can sample like very finely or very coarsely as maybe you want. You can do something that's adaptive. But the main point in this case is that you have continuity in both space and time, and you can impose that afterwards, depending on your solution. And then the other points, like you encode once, and you just run for as long as you want. So the latent space in this case, you will see are weights of a neural network. And this is kind of the main difference with other approaches. For the encoder, this is kind of the main issue here. You have to somehow have some smoothness incorporated in the encoder and be able to control the Lipschitz constant. And this other, this system down here, it looks very nasty. But actually, if you have the trajectories in latent space, you can use what they call a neural ODE to do this. So neural ODE is just basically a backpropagation scheme that you can run with Runge-Kutta. So if you have trajectories of these type of things, you can learn the dynamics fairly efficiently, provided they're smooth. If you're not smooth, it becomes much harder. Okay, so now how it works. So you have a snapshot. You will sample at some point. Then with these samples, you will generate this weight. So this is a cartoon of a neural network. And then when you have this weight, then you can add any x here, and you can recover the snapshot. So particularly, if you have this x, you encode, you have this weight, you impose the same x here, and then you see what the value this would be. This should be fairly similar. So it should be basically an autoencoder. The difference here is that the decoding itself is the network. So you don't have through, if you've seen Olga's talk, that normally you have your, let's say, u, x, comma, t. Then you have some theta. And then you have something like this. This is like u, x, comma, t, or approximated. So in this case, this decoder doesn't exist. You decode a one shot by sampling and currying this neural network. So then how it works, so you will have this weight here. Then you have a dynamical system for this, so you can just integrate it. So the networks are going to change, and therefore the snapshot is going to represent different snapshots, and then you just continue until you get to the end. So what is the advantage of this is that you can build your network to satisfy the conditions that you want. So in this case, you will have very simple like a periodic boundary condition, so you can just
I just wanted to slow you down a bit. So can you just go back to the previous slide? Just, you were a bit fast for me. No, the one after. Yeah, so what is the input here to your neural network? Is it the spatial coordinate only, or is it something else?
It's the values of this point.
So it is the values of the function at those points.
Yes.
For at any point in space. So you do pass the coordinate or not?
So yes and no. What we represent u is on a uniform grid. So you don't need to add the coordinate, but you can actually have a graph. Represent a graph. Use a graph neural network to give you the points. The difference if you use graph is that it's not sure that you can satisfy Shannon-Nyquist. So if you have a graph through its two cores, you only have an estimation of the function, not the function itself.
Okay.
Is that clear?
Yeah, to me it is clear.
Okay.
But I think you should go a little slower in this slide.
Okay. Questions? Okay. No questions. Okay. So again, let me rephrase this again. So what you will do is actually let's put it on. So what you're going to do is going to go and sample. For example, you have this ux, so you have some points. So you're going to have ux, let's say 1 of 0, ux2 of 0, ux3, 0, ux4 of 0. Then you will basically put them in a vector, ux1, 0, ux2, comma 0, ux, I don't know, little n, no, let's capital N, comma 0. So this is going to be a vector of inputs. Then what you will do, this will go through this encoder here that I will talk before. So this is exactly uxi0 from 0 to capital N is what you have here. And what is it going to generate this guy is this weight. So let's call it theta. I don't like theta 1, theta 2, theta. Theta. Yes, well, just call it theta for now. And what are these? Okay, so this is what you have. And then what you'll have is a neural network. So you will have an input, let's call it x. And then, I mean, this is your favorite picture for now. So you have, let's call theta 1 here, theta 2, theta 3, theta 4, and then you have, I mean, it's, I don't know, I mean, just drawing something randomly here, theta 5, theta 6, theta 7, theta 8, theta 8, and then you can go just, and the output we will call theta x. So basically you input any x that you want, you go through this network, and then you have this, and what you want is that this guy has to be approximate your initial function that you start from, ux, 0. Is that clear? Yes, no? Okay. Now, the point here is that this is only for one time step, right? So this is only from t0. So that's why you have theta of t0. So then what you want to do is basically evolve these guys. So this is, we'll call it theta t0. And then you want to evolve this guy to theta t1, for example. So now this is going to be a theta, a new theta, a different one. Yeah, well, let's put it like in green. And then instead of approximating this is going to be t1. And this instead of approximating u of u of x, 0, is going to be t1. Right? Now, is this clear? Is it better? Can I go forward? Yes, no? Okay, we'll assume that I see more noddings than nons, so I will assume that it's good. So this is basically what this shows. So you go further, and then as you can see, as your weight represented in these colors change, your snapshot representation also change, and you go to the end. Now, the advantage of this is that this network, you can play any shenanigans that you want with this network. Because you can, if you have something you know there's going to be a discontinuity, you can add it. If you know there's going to be periodic, you can add it. So in this case, follow what Sid was talking yesterday, you kind of fix your approximation space. And you know that everything is going to be into this approximation space given by the architecture that you choose for this particular network. Questions there?
Hello. The main idea of the new theta t is that it's going to become continuous in time and space, the dynamics.
Yes.
But yet, while training it like this, it's still discrete in a sense, because you still have this theta evaluated at t1, t2 until tn.
Okay. Yes. So I will go into that in a moment. So that's a very good question. So let me rephrase it. So the problem itself is continuous, but you only have data at particular time intervals, right? So what you will do is basically you will evolve, and then you will compare your data. You evolve, and you compare your data. But then at inference time, you don't need to stop in the middle. You can just like unroll until the end, until the horizon, and then you can actually go to ambient space. Well, sorry, is that clear?
So you go discrete until a certain time, but then you evolve until you have this theta t, basically.
Yeah, because in this case you can use an integrator. So you can, if you have like normal prints or whatever, your favorite integrator, you can just go. I mean, you don't need to stop there if you don't need to.
Mm-hmm. Okay.
Is that clear?
Yes.
Okay, perfect.
This is probably anticipating, but you fix the architecture once and for all, right?
Yes. So that's kind of a little bit of the art. So you want an architecture that is expressive enough that you can represent everything that you will be thrown upon.
Yes. Okay. So it never changes because it would be beautiful to make it evolve in time if needed, but.
In theory, you can. You can have a more general hypernetwork that basically is going to change your architecture on time. But the problem is then you basically include discontinuities. Right? Because I mean, suddenly you have another weight here that wasn't before.
No, well, I was rather thinking the opposite. You have a fully connected one, but you want sparsity. Therefore, you zero out a bunch of them for a while, and then you only activate them at a certain critical time. I don't know if this is possible.
You will see that actually is exactly what happens.
Ah, great.
So you could see something that's very, very zero, and then suddenly upticks when you have, for example, a shock.
Okay. But so do you really in your, okay, but it means you put zeros and there you compute the gradients of these nodes, which is not a sparse structure, right? Your structure is fully connected with zeros. It's not the same as having the sparsified structure.
Yes, and exactly. So it's still,
okay.
There are zeros, but you don't, okay, yes and no. So the issue here is like, that's for training. But when you take inference, you can have basically zeros, and you can basically, this theta dot here basically can be zero in some of them. But the point is again, is that you don't want to discontinuity. So you don't want basically have basically something that is not connected and then connect it again.
Ah, okay. Okay. That was precisely my question. Thank you.
Yeah, it's about the initial data.
Mm-hmm.
Imagine you have a time series, so at each time you have just one observation. What can you do in practice? Is it still usable or not?
I mean, the problem you have one observation, you don't have enough real information to create a unique weight, right? So it's going to be a sequence of weight that you can generate. So in this particular framework, you will need a probabilistic approach. In this case, we suppose that we have enough information to basically reconstruct this T and actually go back.
Okay.
I don't know. Did I answer your question?
Yeah.
Okay.
Okay.
Okay. Now, while the microphone is rolling, any more questions? No? Is this clear? No.
So, something I'm still not clear is I was thinking about, like, you were doing this with the previous approach. So I basically in the diagram in the one that you said that can become unstable.
Mm-hmm.
I don't get what are the arrows that go from one U to the other. So I was thinking that the U's would be like more of a query rather than something important in the dynamical system. Could you maybe detail that?
So if you understand correctly, is this versus this.
Yeah, right.
So
I guess so.
Okay, so the main issue here is that every time that you go back and forth, you make a mistake. You can make a mistake.
But why would you do it in the first place if you are evolving the thetas, right? I mean, to me, it looks like a query, but I guess there is something going on with the orange arrows, maybe? I don't know.
Okay, fair enough. So what happens is normally when people do this type of things, normally these operations are fused together. So it's one full operation at the same time. So you have a latent space that you compute. Basically, just imagine you input something, and then you will have a latent space in the middle. But again, you never do just this latent space representation by itself. You can basically go back and forth. No, I didn't answer your question. So, okay, so let me put it this way. The main example that I can give you is like DeepMind forecast methods. So what they do is they do exactly this. So they go from one part of the atmosphere to the next. But if you take a look at what is going inside, what they do is basically, this is in a mesh. So they take the mesh, they go to a graph. They have some representation on the graph that is basically this guy. They process the representation of the graph, and then they sample back into space. They don't do just this guy because the representations may not be unique. So you have to consider also the uniqueness of these representations that they may not be unless you do something else with them.
Okay, right.
Is that clear? I mean, is that clear? Did I answer your question?
Yeah, I think so. I have to think about it.
I mean, you could, in theory, I agree. You could just stay in latent space and roll this in time. But what people, they don't tend to do it because if you just roll in latent space, it becomes even more unstable. And I will present in a little bit why we think that's the case and why people basically, in general, choose to just go back to the ambient space.
All right.
Because if something goes wrong, you can see it, right? You can see, for example, I mean, I don't know, you have a discontinuity that's firm, you can see it right away and say, well, correct that. Where if you just evolve in latent space, you have no idea where it could be going on.
All right.
Is that
Yeah.
okay?
Yeah, that works for me. Thanks.
More questions?
Just to make clear, could you go back to the next slide, please?
This
if
one or back or
next? No, next, the one where you are explaining your network with the yes. Thank you. If I understand correctly, we are training n different neural networks, one for each time step.
You can think about that like that. But you trained only the weights. If you don't train them, basically you evolve them. So you can think that for every time step you have a different network. Now the question becomes how to generate those networks for each time step. And what I claim is that you can create a dynamical system that will, if you solve it, if you integrate it, it will give you exactly the weights for that particular network.
Okay, and so it's an all combined process. You don't firstly create the network weights and then see how they evolve.
Yep.
Okay.
And then you make sure that as you go further, you're actually approximating what you have to approximate.
Okay.
So again, this is exactly Fanny, no?
Yeah.
Fanny says it's basically for each time step you have a new network. The problem is how you generate this network without having to go like a pins or have to entrain for all of them at some point. What I reckon here is like you can create a dynamical system that if you integrate it, it will give you exactly the weights that you want. More questions? Now the microphone is in the middle. I think there's another question there.
I wonder how would you find the dynamic systems for the weight?
You will see in a moment.
Oh.
But I mean, okay, this is when I was telling you a little bit of the tools. So the tool that we leverage here is something that's called neural ODE. So what it does is basically, if you have data, you can actually fit a neural network to that. You can train this gamma beta to fit those things, provided that is done regular enough and it's not high dimensional. You can do it pretty well.
There's another question from the Zoom. So could the instability observed when evolving the dynamical system on the latent space be related with the stability properties of the time integrator?
Yes and no. So there's one inherent instability. When you do this latent space, actually given that the representation is not unique, you can have different ways representations. So you want to choose one that is nice. And that nice will be made apparent, like it will be clearer in 2 or 3 more slides. The stability with the integrator, yes, but that also depends on your gamma beta. If you have something that is reasonably good, like a dormant prince, you can basically adjust your time step. So you have accuracy and to a degree stability. Questions? Another one there. I mean, people at least are awake, so that's good.
Okay, thank you. I'm kind of confused about your evolution equation on theta.
Mm-hmm.
So is it like a local equation or a global equation? I mean, in the end, you will discretize it. So if it's local, it will take into account the previous state or all the story in the past. That is my question.
Okay, so is it local? Yes, in the sense that you only approximate the instantaneous derivative of theta. So that's what you want to approximate. Now, it's global in the sense that you have to integrate it. So it will be a discretization at the end of the day. But the discretization is only chosen after you have inference. So is that clear now? Okay. I mean, you train these guys, you have a beta, and then when you solve like an integrator, like a Luca or like an Euler, the only thing that you need to ask is basically kind of have access to this gamma beta, and you do have.
Okay, but maybe to reformulate my question, you could also imagine that you introduce some delay in the equation.
You introduce
at the moment in your.
There's no delay. I mean, okay, fair enough. So if you have a multi-step integrator at the end, you will have some delay because, I mean, delay, you won't only depend on theta, you will depend on theta in a few moments behind. But that is integrator part. So as long as you have this expression, this is completely agnostic to the integrator that you use at the end.
I think the question is, can you add another delay term to that equation?
Okay, yes, but in this case, you assume that your system is autonomous. So only depends on the, basically you can see this is Markovian. So you only depends, the next step only depends on your present state. So you don't need to add anything else. I mean, you could, but it's just redundant. Did I answer your question? Okay. So it's a very good point. So in this case, we suppose that we have an autonomous system, which is basically the assumption that we have at the beginning. Okay, questions? No? Okay. Okay, let's continue. Hopefully everything is clear now. Now is a little bit more the details. So there's many ways to build this network. For us, all these problems, we know exactly how to solve them. And in 1D, periodic boundary conditions, okay, a question to the audience, given that I'm being grilled here. What is the best method to solve those PDEs in a 1D dimensional setup with periodic boundary conditions?
Fourier spectrum method.
Exactly. So you do Fourier spectral method, or pseudo-spectral, if you're in the US, to solve these guys there. So we know already that Fourier space are very, very efficient to do this. So this is where a little bit of math comes in the way. So instead of trying to do something very exotic, like a transformer or anything like that, let's do just a Fourier ansatz. But the problem is, like, you don't want to do Fourier ansatz because you have to somehow compress this a little bit. So you will do it simple. You will add your Fourier domain. So as you can, well, your Fourier coefficients here, Fourier functions, and you will do a nonlinear perturbation. So you will take this guy, and you will just, instead of your constant be a constant, you will have a constant that depends on x, and it depends on basically theta. So you build, again, a Fourier ansatz, very low frequency. So in this case, you have like 3 terms, and then you add a nonlinear correction to that. And the nonlinear correction is just very easy MLP, just a dense linear network that goes in the middle. You want to add periodicity, so basically the inputs of this phi k are just these sines and cosine features. So this is, again, fairly standard. And this was already introduced by Kai, Li, and Liu. They call it the Fourier split architecture or something like that. So anyway, this is fairly simple. Just think about a very low frequency Fourier ansatz in which you just slap a neural network in the front. Yes? No? Okay, this is kind of the simplest thing that you can think of, and actually works remarkably well. So, okay, so we have our ansatz. Now let's try to train it. So what you want is basically, you imagine that you have this directory of views. This is what you want. And then you want to basically take this thing and generate a latent space. And what you like is that something very smooth. So that is nice. So why this is good is because if you want to integrate something that is very smooth, you can take very big steps and make very small errors, right? I mean, this is basically Shannon Nyquist for an ODE. The issue is that if you're not careful, and actually, most of the time, if you just don't do anything special, you will obtain something like in the right. So you compress. Okay, you can compress quite a lot, but the problem is that when you try to evolve in time, you have these very stiff, very high frequency problems. And then if you try to do a time stepping with this, you have an issue because you have to have a very fine step in time to actually capture these things accurately. So if you were to just integrate this, you have to do very, very small time steps. Otherwise, you can like overshoot completely. But in this case, this is so smooth that you can just like take 3 or 2 time steps, and then you can arrive to the end together. So the point on this slide is that going for very, very high compression, normally you will end up in the right side. So this is very sort of like was seen in Twostage, that you can compress everything like to 3 dimensions, but then it's completely unstable. So basically, you want to evolve it, it's going to be very, very hard to capture. So what I reckon here is that you can go in the middle. So in general, you have a lot of slack in this case because you will be a little bit over-parameterized, but you want to be over-parameterized in the good setup. So basically, in this right one. Now, the problem now is how do you enforce to the network to choose the left path and not the right one? Okay, is this clear? Yes? Okay. So this is another step we will see in a bit. So basically, this is the thing. So you can pursue, if you pursue the higher compression, you can end up in the right figure. If you don't, you can still go into the right figure because the representations are in general not unique. So you see somehow to encode in a way that is somehow Lipschitz stable. So how this is done? This is basically enforced during encoder training. So this is another point that is very important. So most of these methods here are normally trained what is called end-to-end. So what do I mean end-to-end? So they try to train everything together. So you start from 0, you encode, you evolve in time, and then you stop at your timestamp, and then you compare. The problem is when you start, your encoder is very bad because you just started training. Your dynamics are extremely bad because it's just starting training. So you can go farther away, and you're not close enough to the pattern of attraction in which you have a good solution. So basically, it's a nonlinear problem in which you know there's a solution that lives around here that is reasonable, but you start from here. So it's very hard to correct everything to this point. So what you want to do is basically massage a little bit this problem. Instead of starting with something very complicated, just focus on step by step and basically get close enough so you can actually go to the correct or some reasonable solution. So in this case, what we do instead of training everything together, we train the encoder first. So this is basically an encoder-decoder type of training, and then we train the dynamics when you have the latent representations. So what do we have the encoder? So the encoder we have is basically we know the trajectory, so we know that's one after the other. And we want to enforce is something very simple. So if you were to use this in reality, you want to somehow be able to commute. So what I mean with to commute is basically, I was mentioning before, you start from this guy, you encode, you evolve, and then you can evolve again, and then go back to this guy. That's fine. But then you can stop in the middle. You can basically encode, evolve. Well, let's go see if that is how we're doing. Then encode again, continue, and then decode. The problem here, like this thing has to basically, if you encode decode, have to give you to the same point. And if you take a look at normal ways of training an encoder, autoencoder is going to be, you start from U, you go theta, and you have to go back to U. But in inverse, you never impose, you have to start from theta, you go to U, you go back from theta, you have to remain in the same point. And that's kind of the main issue. So if you enforce that, this is a very simple way to ensure, or at least nudge, the system to make this scheme, this diagram to commute. And how we do it is very simple. And it's embarrassingly simple, but embarrassingly useful, is that instead of having the typical loss function of the autoencoder, so this reconstruct is, if you've seen anything like that, this is exactly what you would do. So you take U, you encode U, you decode, and you have to go back to exactly what you had before. So this is the regular autoencoder. So what we do instead is add another regularization in which you do the opposite. So you start from theta, you decode, you encode, and you go back to theta. So this basically is like a symmetric formulation. And this is done fairly, very frequently for video generation and generative modeling. But to our knowledge, it was not used in this context. And why this is useful? Because of the following. So if you suppose that you have an ideal method. So basically, you have a correspondence between U and theta. So U is just this decode theta. Theta is the encoded U. If you compute the time derivative, first year calculus, you will have the expression above. But in this case, you realize that we really don't have access to U prime because we're not training the dynamics yet, and actually we don't know what U prime is. But let's suppose that we have it. Then you do a fairly standard algebraic manipulation. So what you do here, basically you have this, this equation, you have this U theta, you just replace that in that one, you obtain this, and then you do this there. So you have these two new conditions that are under several assumptions of regularity, they're equivalent. But then what is this? So the left expression is nothing more than the time derivative of the encoder. So if you have U has to be decode encode U, you take the time derivative and you obtain that expression. And the same thing from U from theta. So if you take theta, you decode encode in theta, you compute the time derivative, and you obtain the second relationships. So what you want to do is basically enforce these relationships without having access to the derivative. So this is way to enforce this thing is basically impose that this holds and this holds. And then if this holds, then you take the derivative, basically it's going to be 0 or a constant, depending. And, but we don't have this because we don't have access to the dynamics. So the easiest way to do it is just basically impose that these two things have to be small. Normally, you would impose only the left one. In this case, you will see a little bit the results. Imposing that the right one is also true, you have some control on the Lipschitz continuity. This is clear. So it's a very simple trick, surprisingly useful. So questions?
I was just wondering, so you have this parameter gamma between the two losses, two components of the losses. So how do you fix that in practice?
Sorry, you mean?
Yes, between the, yeah, here
this
you have
gamma.
this gamma, yeah.
Okay. It's a very bad answer. You just try it.
Yes, okay, for sure. Yeah, that's what I was expecting.
Okay, I mean, there's a, okay, so it's not true, just try it. So basically what you have is like these guys are a different, have different dimension. So the first thing is that you try to be sure that the dimension actually match. Other than that, is it depends how much smoothness you want on theta. So that's another thing that you can regularize.
And you do this loss function over every observation point, right?
Exactly.
Okay. So it's summed over all the time steps.
Not all the time steps, but the ones that you train.
Observation points.
Yeah, that is another question there.
Just a question, like, so does this consistency loss enforce a smoothness condition on theta? I don't quite see how it enforces a smoothness rather than just consistency.
Okay, so there's two things. Like one is smoothness. In the sense, this is going to be smooth because you can create, you can basically make sure that all the weights are smooth. Sorry, all the actuation functions are smooth. Mm-hmm. So you can make the network to be as infinity as you want. Okay. The problem is this is like basically how do you reduce the TV norm basically. Okay. And that I don't have an answer. I mean, okay, I do have a partial answer, but then basically you have to go through this. You have to go through these same ODEs. You have to assume that you have a lot of regularity, and you can claim that at some point you will actually have you reduce the variance, or you reduce the TV. You reduce the Sobolev norm. Sobolev, I mean, in the second derivative, I think.
What's to prevent us from just having, okay, this like super wild max compression still satisfies these consistency criterion?
I mean, you have you have a conservation of information, right? Yeah. So if you have like a time snap, both in space and time, the amount of information has to be constant. So if you compress too much in space, you have to somehow leeway in time as well.
My question is rather this like crazy oscillating max compression. Why doesn't it also not satisfy this consistency condition?
Well, there's two things, right? This is not a condition that you have to satisfy. This is going to be something that you want to minimize.
Yeah, so why can't that be just a minimum for that?
Because it's not, this is a neural network, so this can be very, very clear. Unless you give an inductive bias as it's going to do whatever you want. Okay. So a priori, if you try this, you won't satisfy this condition. I don't know if that satisfies your question.
A bit, maybe.
So okay, that's the point. I mean, these are a little bit of the Wild West or all these things. So if you don't tell the neural network what to do, given that very expressive, it will do whatever it wants. So you have to basically tell it, no, dude, go in that direction. This is the good point to follow. And you will see in a moment. Okay, just another.
So I imagine your consistency loss is something with which you can break the symmetry in the weight space. And that's what's contributing to the stability in time, indirectly, I think.
Sorry, what do you mean with symmetry?
So basically, in the weight space of neural networks, you can obtain the exact same solution by permuting the weight matrices. So for the same neural network, you can have lots of representations. And I think with your consistency loss, you're saying basically that if I start from parameters theta, I decode and I encode, I have to find the same theta again.
Exactly.
I think that's probably a way to break the symmetry.
Okay, yeah, I mean, at that time I completely agree. So basically what you try to do is, as was mentioned before, you try to enforce some kind of like literal stability. So you go back and you got forth, you have to get the same, exactly same number. You can get something different for sure, but in this case you try to enforce it, so it's the same. Very good. Okay, questions? Have 5 minutes, okay, so 10. Well, do we need question at the end? I think that we have more than enough.
Then you can take 15.
Okay. So now, what is left? I will try to convince you that actually this works. So this is the main indication here. So we do train these things for latent space. I don't remember if this is Kuramoto-Zivashinsky, I think. So if you don't take any regularization, you obtain things on the left. So you can see these the scales in y is quite different. So you have like minus 50 to 50, and the others like 1 and 3, minus 3. So you do have quite a lot of things kind of squish in the middle. And as you start to add more regularization, you can see that basically you become smoother and smoother. So if you try to basically integrate the one on the left, you need very, very small time steps. If you want to integrate the one on the right, it's like 5 time steps, and basically you arrive fairly well. And what is surprising here is that normally when you do regularization, it's a trade-off, right? You regularize something, but your approximation becomes worse. In this case, surprisingly, it's not the case. So as you increase, okay, let me do a thing like this. So in this one here, basically you have, what is this for? Okay, so each color is different learning rate. So we try, I think, like, I don't even remember, like 10 to the minus 3, 10 to the minus 4, 10 to the minus 5. So if you don't have any regularization, you will see that, if you have, the solid line is the reconstruction, and the dashed line is the consistency. So basically you will observe, if you have this type of regularizations, is that, here, so if your regularization loss goes down, normally the reconstruction will go up. This is the typical things that you see, because basically there's a trade-off. In this case, surprisingly, as you increase the regularization, actually your reconstruction loss actually goes down. So basically you're pushing the network in not only a better, not only to converge faster, but actually to converge to a better solution. And this is always surprising for us. Now, the dynamics. So I won't spend too much in this. So basically what you do is you create, you have all your trajectories in real space. You create a bunch of trajectories in latent space. And the only thing that now you have to learn is basically approximate this gamma beta. So the way to do it is what we call an ODE type of loss. So what you do in this case is very simple. You start from, for example, theta t0. You integrate to a certain theta t n, I think, and then you basically just compute the difference and then to minimize. So how this works is basically someone already coded this thing. So what is going to happen is that the integral, you can think it as a multi-layer approximation, and what you will do is just do adjoint state methods in that. So this is fairly similar, I guess, like a Brun and company that works in wave propagation. This is basically how all the inverse problems work for wave propagation. And the advantage here is like your gamma beta is a neural network. Now, this is starting to be a little bit the state of the art. So what you want to do in this case is a UNet for the neural network. The issue is that you don't have a grid. Theta are just weights of a network. So there's no topology. It's like no sense of left and right if you have a weight space, for just a weight. But what you have is basically the computational graph. So what do you mean computational graph? It's basically these guys are connected by these two, this by that, and so on. So you have a topology induced by the computational graph. And that gives you basically a sense of distance, basically the distance on the graph. And you can use that to grade your UNet. So you can see like you have weights that's just like a local, and then you consider approximation by layers and global. So this is the simplest way to do a UNet style based on something that has like a non-Euclidean topology. Okay, that's not clear. Yes, no, yes, question. Sorry, what? So I mean, this integral, okay, so if I understand correctly what the integrals come from. So this is just, recall that what we have is, we'll go back. We have this. So what we will learn is, this is basically what we want to have, this gamma beta. But we don't have access to theta dot. We don't ever have access to the derivative. So the one way to do it is basically, you can integrate, and now you have access to snapshots. So you have basically theta 1 here, theta 2, theta 3. And what you want to do is basically integrate theta dot in time using this thing, and then you can compare at that point.
So it's like theta is already approximated.
Yeah, the theta here is sort of the one that already, so there's two steps. You first encode all your, okay, let me see if I can answer you without writing. What we first do is you have all these trajectories, this U, you transform everything to theta. And then what you do is you learn the trajectories in theta. That's it. Is that clear? Okay. No?
Here.
Yes.
Could you just repeat where is the computational graph arriving in the business?
Oh, okay. So when you define your, let me go back. So when you have this theta, you see this have interconnectivity. So this is, you can say, like a computational graph. So basically, all these weights are connected by things that are close by in the computational graph. So for example, these weights here are connected directly to these ones, distance 1, you have one edge, distance 2 of these ones. So in this case, you basically define a distance topology into the weights.
And is it useful to compute the integral? Where do we need this topology in between the weights?
Okay, the topology that you need is to basically define a UNet. So UNet, so UNet normally what it does is basically you have a vector here. The topology here is a typical Euclidean topology. So basically, this guy is next to this guy, is next to this guy, and then is farther away from this. So you're going to do is that you can basically build, you take like the ones that are distance 2, and you put them together. Then you have another level, the ones that are distance 4, for example, like I don't know, like this one with this one, and you put them together, and you process them by distance. The problem in weight space, these theta are weights. You don't have a sense of distance per se, because those are weights. It doesn't represent anything physical.
Okay.
So you need to basically find a notion of distance. I mean, you can have different notion of distance, but we realize that this is kind of the simplest one, and we can argue that it's something that is reasonable. Did I answer your question? Yes, no? Okay. Continue. We don't have that many slides, so it should be fine. So just I will give you results. Hopefully I can convince you that this is a good thing to do. So this is our test snapshot of these our 3 problems. So what is it called? Space is in that direction, time is in the other. So we trained this only for a very short period of time. So basically, I think this is supposed to be 10 units of time. We only train until 2. And all the rest is just a rollout after the horizon. So this is some of the questions that I had before. In this case, basically, you just train until a few time steps, but then you can continue, and you're still fairly good. Now, to the right, we implement a few different things. So we implement DeepONet, we implement FNO, we just have DMD. That is, we know that's not work, but still we wanted to show that actually, that we know what it is. Neurogalerkin, so this is Benjamin Perstoffer idea that I think Olga also mentioned too. I think Olga have a project with that. Or someone has a project with neurogalerkin. Which project? Neurogalerkin. I think someone has a project with neurogalerkin. So we implemented that with different sampling methods. And what we have, okay, there's 2 metrics here that we have. The first metric is just the root mean square error relative. So this is just L2 distance. But the issue in some cases, for example, Kuramoto-Sivashinsky, is that this equation is chaotic. So even if you use just a regular problem, you perturb a little bit, you have a completely different, different realization, different solution. So it doesn't make sense to really compute the RMSE because you know that it's gonna be good until you hit the Lyapunov exponent. So instead, what you want to do is basically check what is called like the energy, the spectra. That it basically tells you how roughly the solution looks like, not necessarily the correctness. You can tell like a statistical correctness of a solution. So we compare these things together. So viscous burger, everyone basically beats these things. It's very easy. We're competitive, but then log energy, everything is fairly good. High frequencies tend to be a little bit harder to capture. Kuramoto-Sivashinsky, then we see some methods fail. So I think like the ones that do great is our methods, and then the neurogalerkin. All the others have some issues, or no, DeepONet, I don't remember. But anyway, we're the best in those 2. But the KDB, basically, everything fails. And we gave it a pretty big shot. I mean, I think that we ran a few thousand different simulations, different training sets with the other method, and we were not able to have one decent, one stable actually snapshot, trajectory. So in this case, particularly with this first wave, having something that is very tailored and very smooth in time actually helps you a lot. Now, hopefully this convinces you. I mean, you have to. You will see the code after you want to play with this. Now, what the inference of the efficiency? This is a little bit hard to compare. We did walk log time, but it's a little bit hard to do. So the point here is the number of function evaluation that you have, so it's NFE. So what is the point of this is that given that you're very smooth, you can take much bigger time steps. So if you have something that is completely adaptive, integrated is completely adaptive, that you let it do whatever it wants to take time steps, using our approximation, actually you need you can take much longer time steps. And you can see the difference here. You have like, I don't know, 18 versus like 90,000. It's a pretty big difference. But again, I mean, if you compare with solvers, I mean, there's no comparison. We're slightly faster, but we approximate 3 digits. The solver will do 12. But again, this is mostly trying to compare against other methods out there. Well, that's what I was telling you before. And now we can do this in 2D. It's not, I mean, this is work in progress and cannot be loaded. Okay, that is great. You see on the slide that I gave it to you, so you will see like some fluids going around. And I guess the next one is not going to, okay, fair enough. So what you should be seeing there is that, okay, I mean, I'll have to explain this by words. So basically, we train this thing in 2D for an average talk. Very simple flow. It's nothing it's a Kolmogorov flow, low frequency. And you can train for like basically times 2. So you just have like a time, all the integration when you do for theta can be between 0 and 2. But then you can really, it's so smooth that actually you can let it run for much, much longer. The trajectories are not going to be great, but it's stable. So you can grade, I feel like 400, and still you don't have anything that goes, that blows up, or I mean, you accumulate error for sure, but you're fairly stable. And this is one of the after, where it was very surprising for us, and after, a condition after having this very smooth latent representations that allows you actual stability. And conclusions, and quickly this is accepted in iClear 2023. We have a preprint there. You should have access to iClear, so it should be fine. And then we have released the code. It is a little bit complicated because you need a lot of weird tooling. But if you want to take a look at basically how research is done, like industrially, you can take a look at this code. It's in JAX, so you have to bite the bullet with that, but give you roughly an idea how you can easily iterate and launch examples, like experiments in parallel very efficiently. And I think that we're out of time, so you can read the conclusion by yourself. Thank you very much, and I will see you after the break.